thank the I want to thank the organizers for inviting me and giving me the opportunity to talk here. And I'm just going to give you sort of a pretty high-level overview of nucleosynthesis. And here's the game plan for the next 25 minutes or so. So I want to give a very brief, just really high-level overview of nucleosynthesis. For a lot of people, this is probably not going to be new, so I apologize, but I want to make sure that we're all sort of on the same page. Then I want to briefly talk about nuclear reaction networks, and especially my own network and sort of how it works. And then finally, I'm going to look at some results from our process calculations, specifically in neutron star mergers. So when we talk about nucleosynthesis, this is really sort of the figure that comes to mind first. And what this shows is sort of the inventory of the abundances in our solar system. And you can see that that spans about 8 orders of magnitude. And on the x-axis here, it's not really element number, but it's the mass number that's shown here. And so obviously the lightest elements like hydrogen, helium, and lithium down here, these were produced in the Big Bang. So those are like the initial conditions that the universe started out with. And then we have stars that mainly produce these so-called alpha elements, which are helium, carbon, oxygen, neon, magnesium, and so on. These are these peaks here. These are basically just different numbers of helium nuclei fused together. But at some point, iron has the most binding energy per nucleon. So really, once a star makes things up to iron, and it builds up iron in its core, it cannot liberate any more nuclear binding energy by fusing iron with something else. And so this is where nuclear fusion stops. And that's also the reason that when then a star either goes supernova, and that's both type 1a and type 2 supernovae, when the material heats up to very high temperatures and pressures, basically it forces the nuclear composition sort of towards iron, because it's just the lowest binding energy. And so this big iron peak that we see here, this is made in supernovae. But then, of course, the question is, what about all the other heavier elements? So if fusion cannot go past iron, how do we make all of these heavier things? And so we need a different process to make those, and that's neutron capture. And that sort of comes in 2 flavors, and I'm going to go through those now briefly. So the 2 relevant timescales for neutron capture is the beta decay of any unstable nuclei that we produce, and then the timescale on which we can capture a free neutron onto some existing heavy nucleus that's in the system. And so in the S process, which is the slow neutron capture process, we basically have very few neutrons around, so that whenever we do capture a neutron onto a nucleus and that then makes it unstable, that nucleus will beta decay before there is time for it to capture another neutron, because we might capture neutrons on the timescale of 100 to 100,000 years. And so here, what I'm showing is just a cross section of the chart of nuclides. So very familiar number of neutrons is increases to the right, number of protons upwards, and then the squares that are labeled, these are the stable isotopes. And so let's say we start with some copper 65, and we have a few neutrons around. So once this captures a neutron, it will make copper 66, but then that beta decays to zinc, whatever that is, zinc, I think, 66, before it has time to capture another neutron. And so the path that the S process walks is sort of just along the valley of stability. We never get more than 1 unstable nucleus away from any stable nucleus. And so these are the nuclei, at least in this cross-section, that the S process can produce. And you note that there are a few which are sort of on the neutron rich side of the valley of stability that the S process cannot make, because basically it would have to capture a neutron onto an unstable nucleus to get there. So that's the S process, and it happens in some massive stars in certain stages of burning where there's a few neutrons that can be released. And so then once that star either sheds its envelope or goes, well, they wouldn't go supernova, but once it sheds its envelope, that sort of can get ejected back into the interstellar material and then be incorporated into new stars. Now, the more interesting, or at least for our purposes, the more interesting flavor of the neutron capture process is the rapid neutron capture process, where basically the R process, where these two timescales are reversed. So now we have lots and lots and lots of free neutrons available, which means we can capture many neutrons onto a nucleus, even when it becomes pretty unstable. And obviously, as we walk further and further away from the value of stability, it becomes more and more unstable. And so the beta decay life, half-life becomes shorter and shorter. But still, we can capture lots of neutrons because there's just so many around. And so we get a path that looks something like this. So again, if we start with copper-65, we capture a whole bunch of neutrons until we make a very unstable isotope of copper. And then at some point we hit what's called the neutron drip line. And that's basically the point where the neutrons are so weakly bound that the reaction of capturing a neutron or a photon knocking off a neutron from the nucleus, these two are in equilibrium. And so you can imagine, that neutrons are almost like dripping out of the nucleus because it's so oversaturated with neutrons. And so at that point, you have to wait for a beta decay here that basically then changes the binding energy of the neutrons before you can move on and capture more neutrons. And I should point out that in reality, this neutron drip line is actually farther away from stability. I just moved it a little closer here to keep the figure size manageable. And also there's not sort of one unique drip line. It depends on the conditions of the material. So like how neutron rich it is, the temperature, density, all that kind of stuff. But, there is sort of this outer drip line, based on the conditions. And then another important thing here are these closed neutron shells. So there are certain numbers of neutrons, which are called magic numbers. And for beyond the iron peak, they're, I think, 50, 82, and 126. If you have that number of neutrons, they basically arrange themselves in what's called a closed shell. It's energetically a very favorable configuration. And at that point, the neutron capture cross-section drops by 2 to 3 orders of magnitude. So once you hit that special number of neutrons, you basically there's going to be a bunch of beta decays before you move past that point because the neutron capture cross-section just becomes so small. And so, of course, once the neutron source shuts off, we make these very unstable nuclides. They're all just going to go decay back to stability. And so we sort of populate the value of stability from the neutron rich side. And so you notice here, for example, that selenium-82, which the S process could not produce, the R process makes, but then this one shields krypton-82, which the S process can make. So here we have an example of two specific stable isotopes that selenium-82 is produced by R process only, krypton-82 by S process only, and it's helpful to have some of these sort of pairs of isotopes that help us disentangle the contribution from the S process and the R process, because most of the stable elements and isotopes can be produced by both. All right, let's briefly talk about that closed neutron shell again, because it actually produces a very important feature in that abundance plot that I showed you. So as I mentioned, the neutron capture cross-section drops when we hit these magic numbers of neutrons. And so that means we get a pileup of material at those, where the closed shell intersects with the path of the neutron capture process. So for the S process, we would get a pileup of material where the closed shell intersects with the value of stability. And then for the R process, we would get a pileup of material sort of down here where it intersects with the neutron drip line. But of course, that's going to decay back to stability. And so that means we get a pileup of material once everything's decayed at a lower mass for the R process than the S process. And so from this, we can basically infer that we expect to see sort of a double peak structure for each of those closed neutron shells, where the low mass peak comes from the R process and the high mass peak in the abundances comes from the S process. And indeed, this is what we see here. So I'm going back to the abundances in the solar system. And now I added the lines that showed the R process in blue and S process in red contributions. And the first magic neutron number of 50 produces the peaks around here. It's a little noisy, so you can't see it very well. But here we have the second peak. And so you can clearly see that the R process has a peak at a slightly lower mass than the S process. And then the same here for the third peak. And this also shows why I think the R process is so cool, because at this peak right here is where gold and platinum sit, whereas the S process just makes lead in the peak, which is kind of boring. But then another important feature is the rare earth elements, which are right here, which are again, mostly due to the R process. And there's some very important elements in there that have, that are important for engineering applications. But so yeah, so this is basically how we can fill in, or how nature has filled in the heavy elements through a combination of the R and S process. And now for the rest, I'm mainly going to focus on the R process, because that's the one that's intimately connected to neutron star mergers. And I should also mention, if anybody has any questions, clarifying questions, please feel free to interrupt me, but there's also going to be time at the end. Okay, so let's look at nuclear reaction networks. So one network that I've developed as a graduate student is called Skynet. It's a general purpose nuclear reaction network. So you basically give it a list of isotopes that you're interested in, a list of nuclear reactions, and then it just evolves these forward in time. And usually when I run it, the data I use, which is distributed with Skynet, there's data for about 8,000 isotopes and around 140,000 nuclear reactions. So that's sort of what's in the network. It's written entirely in C++, but it has Python bindings, so it makes it extremely convenient to use, because you can just basically set it up from your Python script where you might be reading in other data in your analysis pipeline, and then just run it through Python and get the results back in Python. And it's all open source, so you can download it at the code at the Bitbucket address here, compile it and run it, use it to do science, and feel free to let me know if you have any issue, or if you run into any issues with it, if you're trying to use it. So here's just one slide on how Skynet in particular, but this really all nuclear reaction networks, how they work. And the quantity that we're really tracking is this abundance, yi. So for each nuclear species I that we're tracking, we define this abundance, and it's just the number density of that species divided by the total baryon number density. And so the total baryon number density is just the number of neutrons and protons, regardless whether they're free or bound in nuclei. And so because the number of baryons is conserved, the baryon number density only changes due to expansion and contraction of the material as a whole. And so if we divide this out, we basically divide out the changes in the number density of individual species from expansion and contraction, which means the abundance is sort of like a normalized number of particles of that particular species, and it can only change due to nuclear reactions. It cannot change by just expanding or contracting the material as a whole. So if we consider one particular reaction, say we have a proton that captures or interacts with a lithium-7 nucleus, and that then produces 2 helium nuclei, then we need to know what this reaction rate is. So let's call it lambda, and it's usually a function of temperature and density, could be some other parameters as well. And so this is something that we need to have given to us. And there's many compilations of nuclear reaction rates, and a lot of times we may have some parts, certain temperatures and densities where it's a measured rate, but usually in a lot of the parameter space that we need, they're theoretical rates, because they cannot be measured in the lab, and especially if they involve very, very unstable nuclides that we cannot produce in any meaningful quantities or at all on Earth. So then these are all theoretical rates. But so we have these rates, and so then we can write down, due to this reaction, what is the contribution to the time derivatives of the abundances of the different species involved in the reaction. So if we look at helium-4, we get a contribution to the time derivative of its abundance as 2 times lambda, and then the product of the abundances of the input species, because the more protons we have and the more lithium we have, the more often this reaction can happen. And then each time it does happen, we produce 2 helium nuclei. And then similarly, for the protons and lithium, each time the reaction happens, we destroy 1 proton and 1 lithium, so we get -1 times lambda on the product of the input abundances. And of course, the total time derivative of helium-4 abundance gets a contribution from every reaction that involves helium-4. There's going to be thousands of them. With lithium, it's maybe not, maybe just tens or hundreds or so, but you can see that basically we can write down this very big system of nonlinear coupled first order differential equations. And what a nuclear reaction network does is basically it solves that, or it integrates these abundances forward in time to see how the nucleosynthesis plays out. And in reality, the system is usually very, very stiff because some reactions happen very quickly, others happen very slowly. And so if you use an explicit method, you sort of be constrained by the fastest reaction all the time, and your time step will be very tiny. So in practice, we usually use an implicit method just that allows us to keep the time step manageable. Here's just to advertise Skynet a little bit more. Just want to list some features that it has. So it includes an extended Timmins equation of state, which basically has an equation of state that takes into account electrons and positrons that are fully, like up to fully relativistic and degenerate. And then for all the heavy ion species, so for all the nuclides, I'm using an ideal gas equation of state, basically, that sort of combines everything together. Skynet can also calculate nucleostatistical equilibrium. So when the temperature goes usually above about 5 gigakelvin, then the reactions of basically taking a nucleus and completely disassembling it into individual neutrons and protons, and the reverse of assembling that nucleus, they become into equilibrium. And so in that case, you can easily calculate what the distribution is. And so Skynet has the capability of doing that. And it also has this NSE evolution mode. So it actually, when you're running a nucleosynthesis calculation and the temperature, and it moves into this NSE regime, Skynet will automatically detect this and then turn off the strong interactions because they don't really do anything because they're in equilibrium, but they just make the time step small. And so that it's not necessary to evolve them. So Skynet will automatically detect that, move into this NSE evolution mode. And once you're starting to drop out of NSE, you will turn on the full reaction network again. And then Skynet also has self-heating. So if you, these nuclear reactions, they release energy that can heat up the material. And so that is being taken into account. And then Skynet also calculates the inverse rates directly from detailed balance so that the inverse rates are basically consistent with the NSE calculation. And finally, there is electron screening that is implemented with some smooth transition between the weak and strong screening regimes, and that applies to both nuclear reactions and the NSE calculation. On the code side, obviously, there's an adaptive time stepping, because once the composition moves closer to stability, your time step can become larger. As I mentioned the Python bindings. It's very modular, so you can easily extend and add more types of nuclear reactions. That has to be done in the C++, of course. Currently, it implements reactive reactions, tabulated reactions, and some neutrino reactions. And there's also some code that comes with it that makes movies. And I'll show you some examples of that in just a minute. Okay, so let's look at some R process calculations in neutron star mergers. And so I want to give a very high level overview. There's many other talks to go into a lot more detail in this, but just, get everybody on the same page. So there's two main types of ejecta that we talk about where R process or any nucleosynthesis can happen in neutron star mergers. There is the dynamical tidal tail ejecta. So once neutron stars get close to each other, they tidally deform each other and then sort of rip each other apart, and they fling out this tail of fairly cold neutron star material that tends to be very neutron rich. And people do a lot of simulations on this. This is a very incomplete list, but the ejecta mass ranges from like 10 to the -4 to maybe a few times 10 to the -2 solar masses. And then after the merger, we probably end up with some kind of accretion disk, at least for a certain amount of time. And that accretion disk can also drive some outflow, either through like neutrino heating or viscous heating or something like that, where we can just drive an outflow off the surface of this disk, where again, nucleosynthesis can happen. And so that tends to be usually less neutron rich, maybe even neutron poor, because the material is higher and has had more time to basically get into beta equilibrium. And the ejecta mass, again, is pretty uncertain, but maybe on the order of a few times 10 to the -3 solar masses. So those are the sort of the two types of ejecta we think about when you think about our process in neutron star mergers. So let me show you what this could look like, and I hope this video sharing is going to work here. So let me open up the first file. Okay, so here, this is now a Skynet simulation. Each little square here is actually an isotope that's being tracked in the network. And obviously the color shows how much of it there is. And this is a very neutron-rich R process. So we start out with a YE of 0.01, and that's the electron abundance, and that's extremely neutron-rich. And as I run this, you will see how it runs up, and these colored bands here, these are the closed neutron shells. So you can pay attention to those as the R process sort of runs up along those. So I'm going to start it. And the time is on a log scale, so it sort of speeds up as we go along. Now you can see how we run up those closed neutron shells. And now about a second after we start, neutrons are gone and everything just decays back to stability. And we sort of get a strong second peak here, third peak and second peak here. So this is the example of a very neutron-rich R process where we have no problem making very heavy elements like uranium, plutonium, all that stuff up here. So let's go to a different example. Whoops. All right, here we go. So this one is now, it starts out very similarly, but the electron fraction is 0.25, so it's less neutron-rich than the first case. You can see the initial abundance is composition is a little closer to stability, but looks fairly similar. So let's see what happens when we run this one. And it still looks pretty similar at the beginning. We sort of run up the closed neutron shell here, but then once we get to the last one, we just sort of run out of steam, or in this case, run out of neutrons, and all we make is a strong second peak. Can't reach any uranium or any stuff up here. All right, let's see. Let's go back to the slides. Here we go. All right. And so here, this plot basically shows the final abundances of the two cases and some others that I just showed you. And so here, we just start with different initial electron fractions. So the red one, 0.01, is very neutron rich. The purple one, 0.19, is fairly neutron rich still. And you can see that the final abundance is about the same. So we make a very strong third peak, second peak. The black dots here, these are the measured solar R process abundances. So that's sort of what we're trying to match. And we get, fairly good match also with the rare earth peak in between. But then once we go to the blue curve, which is a Y of 0.25, we just suddenly cannot reach this third peak anymore. Thank you. We make a strong second peak, but can't get to the third peak. And then the colored bands here are the lanthanides and actinides. These are very important for the potential kilonova light curve that you get because they have very high opacity. So if you make those, you're sort of going to get like a dimmer, redder infrared kilonova. And if you don't have them, then you will get more of a blue, brighter kilonova. And there's going to be other talks specifically on kilonovas as well. Okay, so this is, in this calculation, we try to mimic sort of the dynamical ejecta. Now I just want to show you some abundances from other types of ejecta. So this is a paper from Jonah Miller et al., where Jonah ran a very good disk simulation. And then he looked at the outflow from the disk, and he looked at them both in like the polar region, which is in blue, and the sort of the equatorial region in red, and looked at nucleosynthesis in that. And you can see a pretty marked difference between reaching the third peak, which we don't really reach in the polar region. So it's just less neutron rich there, but we do in the equatorial region. And then here is very briefly another study where I, together with some collaborators, looked at nucleosynthesis in a disk around a hypermassive neutron star, depending on how long the hypermassive neutron star survives. And so I'm going to skip this slide in the interest of time. Here's the actual results. So here the tau is the lifetime of the hypermassive neutron star. And so 0 just means it collapsed to a black hole immediately. And 10 milliseconds means it was around for 10 milliseconds and then collapsed and so on. And you can see that there is sort of a dichotomy. If we have a very short lifetime, the purple and greenish curve here, we sort of do get a strong third peak. But if the lifetime is like 30 milliseconds or longer, that one's suppressed by about an order of magnitude. So if we could measure those abundances from an actual R process event, maybe we could infer something about the lifetime of the high mass neutron star. But obviously, measuring individual abundances from one event is extremely hard. But just in principle, there may be an imprint of the lifetime of the half mass neutron star onto the abundance. And then finally, I want to just mention another study that I did with some other people where we looked at the ejecta from a neutron star black hole merger. And of course, in many cases, you don't get much ejecta or anything from a neutron star black hole merger because the neutrons just get swallowed whole. But if the spin of the black hole and the mass ratio are just right, you could actually get quite a bit of ejecta, like maybe like 0.1 or 0.2 solar masses. And so what we did here is we took this ejecta, run Skynet on it, and we varied the neutrino luminosity from sort of, again, the central kind of disk object, and see if that has an impact on the nucleosynthesis in the outer part of the ejecta that's expanding very fast. And what we found is that it basically doesn't. So here there's, 2 orders of magnitude difference in neutrino luminosity. The abundances, after a mass of like, I don't know, 100 are basically indistinguishable. And so we get a very strong third peak here. So a very strong R process in this case. All right, and so let me, I just want to mention one very brief thing on uncertainties. I mentioned briefly at the beginning, we need a lot of theoretical data for these nucleosynthesis models. And so they come with huge uncertainties. Got it. And so Matt Mumbauer did a very good study on looking at propagating these uncertainties to the final abundances. And so this is what you see here. And you can see, in the final abundance, this is in different mass models. And there's big uncertainties like 1, 2, 3 orders of magnitude in the final abundances, even if you just vary the masses sort of pretty slightly. So that's why things like FRAB are really important, because that will help us on reducing those uncertainties, but they will still be there. So that's something to keep in mind. Okay, I think I'm just going to leave my conclusions up here and take some questions now. Thank you.
Okay, thank you, Johnny. And let's see, are people raising their hands yet? Okay, I don't see any raised hands at the moment. So I'll take the chair's privilege and ask you to expand for a moment on one of your last points about the effect of different neutrino luminosities in the black hole neutron star case.
Yes. So basically what we found is I'm hearing an echo now. What we found is the dynamical ejecta in this case is expanding so rapidly. I forget the exact number, but it's like 0.2, maybe 0.3 C, that the neutrino luminosity from the central disk doesn't really have enough time, if you will, to alter the neutron richness of the materials as it's expanding. It is, and actually, I think I do have that figure here. Yes, so this is actually the electron fraction distribution from with the different luminosities, and you can see that in the blue case where we have the highest neutrino luminosity, we do get much more material that's more neutron poor, so that where the electron fraction is pushed up to like 0.25 or so. But because any electron fraction below by 0.25 makes basically the same R process, this doesn't really have an impact on the nucleosynthesis. So it does increase the electron fraction in the ejecta, but it can't do enough. It can't really push it beyond 0.25 to have an appreciable effect on the nucleosynthesis in this case.
Okay, so a question from Yosef.
Hi, John. It's a nice talk. I have just a small question. All these R process abundances you present here based on particles in the simulation, or just you calculate the dynamical time and entropy and just estimate the abundances?
So it depends on the results that I showed. So in this case, we really took we assumed some analytic density profile, and basically this was parametric study where we set the initial electron fraction, the initial entropy per baryon, and then some kind of time scale in which it expands, and that's how we get the final abundances. In these other cases, these are actually tracer particles from a hydro simulation. So Jonah Miller ran the hydro simulation, put in tracer particles. He gave me those histories, and then I ran the nucleosynthesis on those. And same thing here, I believe, and definitely same thing here. Does that answer your question?
Yes, thanks.
Awesome.
Okay, and Luciano?
Yeah, hi. Thank you for the talk. It's very good. So I think in slide 15, you showed the abundances for different YE.
Yes.
Yeah, that one. So have you done the same exercise but with different other conditions like different entropies and different densities or that other thermodynamical properties?
Yes.
Does it change that much? How important is the different the other properties?
Yes. So excellent question. And yes, if you look at this reference, that's basically exactly what we did. So we looked at a grid of initial entropy, YE, and expansion timescale. And what we found is for a large range of sort of reasonable entropies, the final abundances are very similar. Once you go to like very high entropies or very low entropies, it changes a little bit. But for what we expect in sort of neutron star merger ejecta, it's a very small impact. Similar for timescales, you have to go to like very short or very long timescales to get a big difference. So in the range of what we expect from neutron star merger ejecta, it's really the YE that's setting it, and it's almost like a threshold function, because anytime you're below sort of 0.25, you make same full R process. Once you're above, again, until you go to like very close to 0.5. But for a good range, you sort of make a similar weak R process. But yeah, I definitely encourage you to check out this paper here, and if you just Google papers by me, you will find that pretty easily. There we go into a lot more detail on this.
Great, thank you.
Okay, and a question from Aman.
Hi, Jonas. Thank you for the talk. I had a question about the slide where you were comparing the nucleosynthesis output to the time of the remnant. If you could go to that slide.
This one, right? Yep.
Yes. What's the YE? Have you fixed the YE, or is it varying over here also?
Yeah, so here the YE is actually coming from the simulation. So Rodrigo Fernandez ran these simulation of basically the accretion disk around the neutron star or hypermassive neutron star and later black hole. Mm-hmm. And so he used basically he evolved the YE in that material, and then gave me those tracer particles. And so really what's happening here, the hypermassive neutron star emits neutrinos. So the longer it is around, the more neutrinos it emits. And because the material starts out very neutron rich, even if you radiate it with the same intensity of neutrino and antineutrino radiation, it just tends to push it towards beta, equilibrium. And so because you start out neutron rich, you will create more protons than neutrons basically. And so any neutrino radiation tends to push it to a higher YE. So that's why it's expected that we don't get a strong R process once the hypermassive neutron star lives long, because you just push the material to higher YE. And actually, I do have the neutrino or the electron fraction distribution here. So you can see there's sort of two effects, like the longer it lives, the more mass you eject, but you're also pushing it to higher YE. So then the actual mass below by 0.25 is sort of the same once you get to 30 milliseconds or more.
Okay.
Yeah.
Thank you.
Yep.
Okay, it looks like we run out of questions. So thank you, Jonas, for a very enlightening talk. And we'll